Section 3.5, Example 4. In this example, we're going to be working with Newton's law of cooling. Newton's law of cooling states that the temperature T of a heated object at time lowercase t is given by T equals C plus the quantity T sub 0 minus C times E raised to the kt power. C is going to be the constant temperature of the surrounding medium. T sub 0, that's your initial temperature of the object that has been heated, and K is a constant, which will be negative. Example 4 states, an object is heated to 100 degrees Celsius. It is left to cool in a room that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees Celsius. Use Newton's law of cooling to find a model for the temperature of the object T after T minutes. So here we see the general equation, and here you see where we have substituted in the values we've been given. So take a moment just to double check and become familiar with those items. So our objective first is to figure out what K is so that we can write the model equation. We have 80 equals 30 plus the quantity 100 minus 30 times e to the 5k power. So we can take care of what's in the parentheses, and now we have 80 equals 30 plus 70 times e to the 5k. Now subtract 30 from both sides. 50 equals 70 times e to the 5k. Now divide both sides by 70, and 50 over 70 can be reduced to 5/7 equals e to the 5k. And from section 3.4, you remember that you can take the natural log of both sides now. So we'll have natural log of 5 over 7 equals natural log of e raised to the 5k. And remember, the natural log of e to the x equals x, so the natural log of e to the 5k equals 5k. So we've got the natural log of 5 over 7 equals 5k. So if you divide both sides by 5, you'll end up with k equals natural log of 5/7 divided by 5. So it's calculator time now, and you'll end up with k is about negative 0.0673. So here's the model equation we end up with. T equals 30 plus 70 times e raised to the negative 0.0673t. Okay, this is what we just found, K. And where does the 30 come from? That is the temperature of the room. And where does the 70 come from? Okay, remember the object was heated to 100 degrees Celsius, and we subtract the temperature of the room. So that's where we get the 70 from. So the next part of example 4, we're asked what the temperature is after 20 minutes. So we have our model equation, and we're going to say T equals 30 plus 70 times e raised to the negative 0.0673, and t is 20 minutes. And now this is just a calculator problem. I'll give you a moment to do this on your calculator. And you should end up with T is about 48 degrees Celsius. Next, we're asked when the temperature will be 35 degrees Celsius. So we start with 35 equals 30 plus 70 e to the negative 0.0673 times t. Subtract 30 from both sides. You'll have 5 equals 70 e to the negative 0.0673 t. Now divide both sides by 70. 5 over 70 will simplify to 1 over 14. And that's going to equal e to the negative 0.0673 times t power. Now let's take the natural log of both sides. The natural log of 1 over 14 equals the natural log of e raised to the negative 0.0673t. So now we have the natural log of 1 over 14 equals negative 0.0673t. Now let's divide both sides by negative 0.0673, negative 0.0673, and now it's calculator time. And you should end up with T is about 39. So it's going to take about 39 minutes for the object to cool to 35 degrees Celsius.